Given an integer array nums, return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. For example, 3627 is a subsequence of the array 0316227. Looking at the first example, we have the input array 10, 9, 2, 5, 3, 7, 101, and 18. The output is 4 because the longest increasing subsequence is 2, 3, 7, and 101, which contains 4 numbers. I'm going to be covering a dynamic programming approach to solve this problem. The essence of dynamic programming is in breaking a problem down into simpler subproblems, and using the fact that the optimal solution to the overall problem depends on the optimal solution to the subproblems. In this question, the subproblems we need to solve are finding the length of the longest increasing subsequence ending at each index in the array. What I mean by the word ending is that the subsequence has to include the number at the index, and it cannot include numbers with greater indices. For example, let's say we're interested in the length of the longest increasing subsequence ending at index 5. These are all the increasing subsequences that end at index 5. Each of these subsequences includes the 7 at index 5 and does not include any numbers from indices greater than 5. The numbers on the right are the corresponding lengths of each subsequence. So the length of the longest increasing subsequence ending at index 5 is 3. Once we solve each of these subproblems, the solution to the overall problem is the longest of these lengths. So we would want to have these lengths stored in a list and then return the longest length. In this case, the answer is 4. To quickly think about why this gives us the answer, whatever the longest increasing subsequence is, we know that it has to end with a number at a certain index. So if we found the length of the longest increasing subsequence ending at every index, we would capture the answer to the problem in the process. So now the real question becomes, how do you compute these lengths? We can iteratively compute these lengths for each index starting from 0 in an efficient way that makes use of our knowledge of previous computations. To understand how this works, consider the following scenario. Assume that we know the lengths of the longest increasing subsequences ending at indices 0 through 4. And we're interested in finding out the length of the longest increasing subsequence ending at index 5. I just want to make a quick note here before continuing. Instead of talking about subsequences ending at certain indices, I may refer to them using the number they end with instead. For example, what we're trying to find here is the length of the longest increasing subsequence ending at index 5. So instead, I might say that we're trying to find the length of the longest increasing subsequence ending with this 7. So how do we find the length of the subsequence? We know that the subsequence has to be increasing, so we look through the numbers at lower indices to find numbers smaller than 7. We find 2, 5, and 3. These are the possible numbers that could precede 7 in the longest increasing subsequence. This means that the number that comes immediately before 7 in the subsequence has to be 2, 5, or 3. Another way to view this is that the longest increasing subsequence ending with 7 is formed by taking the longest increasing subsequence ending with either 2, 5, or 3 and extending it to include the 7. However, we aren't interested in finding the actual subsequence, and we weren't given what these subsequences are. Our goal is just to find its length, and what we do know about these subsequences are their lengths. In other words, we know that the longest increasing subsequence ending with 2 contains one number, the longest increasing subsequence ending with 5 contains 2 numbers, and the longest increasing subsequence ending with 3 contains 2 numbers. And we also know that the longest increasing subsequence ending with 7 is an extended version of one of these subsequences. By extending a subsequence, we are just adding one more number to it. So the length of the longest increasing subsequence ending with 7 is found by adding 1 to the longest of these 3 lengths. In this case, the longest is 2, so we add 1 to find that the length of the longest increasing subsequence ending at index 5 is 3. At this point, we know the lengths of the longest increasing subsequences ending at indices 0 through 5, which means that we can now apply the same logic to find the length of the longest increasing subsequence ending at the next index, which is index 6. And this is how we'll be able to iteratively compute the lengths. To formalize this logic, the length of the longest increasing subsequence ending at an index I is 1 plus the longest of the lengths ending at lower indices that contain a smaller number. In simpler terms, this boils down to looking at the number at index I, then finding all the smaller numbers to the left of it, then looking at their corresponding lengths and adding 1 to the longest length. In the case where none of the lower indices contain a smaller number, the length is just 1. This just means that the longest increasing subsequence is just the subsequence that only contains the number at index I. Now let's quickly walk through how this algorithm would iteratively compute the lengths from the beginning. First, we create a list called lengths that is the same size as nums and contains only ones. These ones are just placeholders. We will overwrite these values as we iterate through the array. Now we start solving for the length of the longest increasing subsequence ending at each index starting from 0. So first I equals 0, and we're looking for the length of the longest increasing subsequence ending with this 10. There aren't any numbers to the left of this 10 because it's at index 0, so the length is 1. Next I equals 1, so we're looking for the length of the longest increasing subsequence ending with this 9. Looking to the left, there aren't any numbers smaller than 9, so the length is 1. Next I equals 2, and again there aren't any smaller numbers to the left, so the length is 1. Next I equals 3, and this time when we look to the left for smaller numbers, we find the 2 at index 2, which has a length of 1. Since we only found one smaller number to the left, its length is the longest, so we add 1 to this length to find that the length of the longest increasing subsequence ending at index 3 is 2. Next I equals 4, and when we look to the left, again we find the 2 at index 2. So the length of the longest increasing subsequence ending at index 4 is 2. Next I equals 5, and we've already done this before, so at this point I'm going to stop walking through the rest of the indices and just quickly fill them in so that we can move on to the Python implementation. Once we've finished doing this process for all the indices, the answer to the problem is just the longest length in this list. Moving on to the Python implementation, first we define a function called length of lis, which takes in an argument nums. Then we initialize a list called lengths, which is the same length as nums and contains only ones. Next, we start looping through each index in nums. In this for loop, we want to find the length of the longest increasing subsequence at the current index I and store it in the lengths list. So we set the value at index I in the lengths list to be the following. There's quite a lot of things happening in this line, so let's break it down. Ultimately, we're going to be setting the length at index I to be 1 plus the output of this max function. So what are we trying to find the max of? Well, we're trying to implement this logic right here. So inside this max function should be an iterable that holds the lengths of the longest increasing subsequences ending at lower indices that contain a smaller number. So here I have a generator expression that has these lengths. If you aren't familiar with generator expressions, for all intents and purposes, this is basically a list comprehension. This expression is saying, for every index lower than I that contains a smaller number, find the length of the longest increasing subsequence ending at that lower index. Now we need to handle the case where none of the lower indices contain a smaller number. To accomplish this, we can simply set the default parameter in the max function to be equal to 0. This tells the max function to return a value of 0 if we pass in an empty iterable. When this happens, we set the length at index I to be 1 plus 0, which is just 1. After the for loop ends, all of the subproblems have been solved. So we end the function by returning the max of the lengths list.